Mm. Ugh. Bouncing between the two microphones attached. Okay. I think that works now. I don't know where the microphone is that it's rolling with, but I think it's working. We're really down to two. Oh. Way down to two. I'm gonna give it a few more minutes in case more people show up. Oh, man. Started work at 5:30 this morning. Came straight here after work to help somebody with math. So now I'm tired. Oh, shit. 4. Ugh. Well, I mean, it got up at 3:30, but I mean, brutal.
Jeez, man, it's good. My job with freaking graveyard. I'm talking about rough. Yeah.
So I wish my job had graveyard.
Really?
That's
No more, man. No more. No more graveyard. It was 10 p.m. to 6 a.m. It's a long time.
that's usually when I'm functional. I'm a nocturnal human being.
Yeah, I had enough. Good 8-9 years straight for that.
That's fair. Mm. All right, well, let's get the show on the road. So for today, we'll do some review of the last class, which is largely scientific notation. Then we're going to get into stuff with lines, graphing lines, finding slopes of lines, plotting points with lines, plotting graphs by eyeballing them. It's not as bad as you'd think. Oh, and this meme cracked me up. Is somebody screenshotted this and I sent it to a friend, and she asked her boyfriend, because he does a lot of drugs, and he had an answer immediately that this is apparently fires lasers. Okay, well, I guess you have to ask one person who does a lot of drugs what the other guy who does a lot of drugs was thinking. And yep, that's apparently gonna fire a laser. I'm pretty sure it won't. I wouldn't feel comfortable putting power into that thing. I think honestly it'd probably just pop, maybe give you a volt, but you know. All right. So we're going to do some review on the scientific notation. So scientific notation, if you recall, it's written in two different parts. You have just the regular digits where the decimal is placed after the first digit. And then you always have times 10 to a power that kind of moves the decimal point around. So the 10 is to a positive high number power, that is going to be a very large number. If it's to a negative power, that is going to be a very tiny number. And it's largely just to be able to work with very large or very small numbers without breaking our brains. That's pretty much its purpose. So to figure out the power of 10, you think, how many places do I move the decimal point? So when the number is 10 or greater, the decimal point has to move to the left, and the power of 10 is positive. And if you're converting that back to a decimal point or decimal number, with large numbers, it has to move back to the right. When the number is smaller than 1, so basically like a decimal, like a small number, decimal point has to move to the right, so the power of 10 is negative. And converting it back, as you'd expect, you go the other direction, it moves to the left. So I figure I might as well have a couple of examples just to show you. Converting that big ugly number to scientific notation, you would be aiming for 4.36 because you want the decimal point after the first number. So you count how many times that decimal point would have to move to the right in order to get past that 4. In this case, it would actually be 11 times because there's 10 zeros and 1 more for the 4. And since it's a very tiny number, the power is going to be negative. So you end up with 4.36 times 10 to the negative 11th. Similarly with the other one, 4.2 times 10 to the negative 7, if you're converting it to decimal. you would look at this and say, okay, well, we have a negative exponent. That means it's a very tiny number. So in order to convert it back out of scientific notation, you would put your pen at the decimal point and move 7 places to the left. And you would just fill in all the little jumps you made with zeros. So you would end up adding 6 zeros because, again, you have 6 places after that decimal point and then 1 more for the place after the 4. So we got a bunch of them where we're converting to scientific notation, converting away from scientific notation, and a couple where we have scientific notation already, but it's not done, it's not finished, it's not in the proper setup. So we're just fixing those. We'll do a couple of each. In the interest of time, I think I'm just going to skip 2 and 4. So we'll do number 1 and number 3. The others I'm pretty content with actually working out. So I'm going to copy those real quick. It's a 1, I promise. My pen just doesn't like me as usual. Okay, so if you're converting to scientific notation, you place your pen where the decimal point is right now. We don't have one here, so you would put it at the end. And you would just start moving to the left and count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That moves 10 places. So we write the number, well, the numbers that matter, which would be the 7, 0, 3, and 1. And that's going to be times 10 to a power. The power is how many times it moved over. In this case, it's 10. And since this is a very large number, this is a positive power. Similarly, on the other one here, we're converting this to scientific notation, but in this case, that decimal point is going to go the other direction. So we end up with 4 jumps, right? And then we rewrite the number with the decimal point where we want it, times 10 to the power of how many jumps we did? 4. But see, this is a very tiny number. We move to the right. So it's a negative power on that. Tiny number, negative power. Big number, positive power. Okay. Then we're going to convert a few away from scientific notation. I'm going to do 5 and 6. So we are converting these guys back into standard decimal notation away from scientific notation, right? So generally what we do, I write out all my numbers, kind of ignore the decimal point for now, and I'll place my pen where it is. Now, we have a 9, there's a positive 9. So that means that this is going to end up a very large number. If it's a very large number, that decimal point's going to have to move to the right. So put our pen there, and we're going to move it 9 times to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we'd be right there. And then all those little hops that don't have anything in them, put a 0. I usually rewrite this without those little hops. Maybe to make it make a little bit more sense, put the commas every third digit. You don't have to, but otherwise I was totally not going to be able to tell that this was in the billions place. This is 1,421,000,000. Because if I don't have those commas there, then it's kind of hard to say out loud, right? So sometimes I put them, sometimes I don't. If I'm just doing my homework and I don't care about how I write this, I don't care how I write this. I'm just going to put it down and call it good. Now for number 6, it's the same idea. Write out our digits. But in this case, the power on the 10 is negative. So that means this is going to end up being a very tiny number, right? So we're going to take the decimal point, put our pen where the decimal point is, and move over 4 to the left this time. So you end up with 0.000628. And technically, to make this proper notation, because you can't just have a decimal hanging out in space, you would actually need a little leading 0 there in front of the decimal. Some teachers mark that wrong, some don't. Technically, is it wrong? Yeah. If you don't have it, technically not done, but everyone knows what you mean. So it's not quite so stressful. Okay. Then we have the ones where we fix the scientific notation. All right. So on number 7 here, we have 206.1 times 10 to the 6th. So we know this is a very large number because of the power on that 10 is a 6. And we also know it's not in proper notation because the decimal point is not after our first digit. So that's what we got to do, is we got to move it from here over to here. So that decimal point would move over 1, 2 to the left. And remember, when we went to the left on number 1, for instance, that actually started adding up to the power, right? So if I am going 2 to the left here, I mean, this is a big number. It's 6 digits over to here, but we need it 2 further. Well, that's going to go up 2, right? So that's going to be 2.061 times 10 to the 8th. 2.061 times 10 to the 8th. So it's not too bad. You just got to figure out which direction the decimal is moving and whether or not this number is going up or down. Similarly, on number 8, we got the same idea, but we have a negative exponent. If I have a negative exponent, that means that decimal would be out here, right? Far to the left. But we need to move that over to here. Very similar to the last one, right? Just moving 2 more to the right instead of 2 more to the left. Well, if that's already 5 digits out to the left here, and we're needing to move it 2 further in that direction, then why did I write 0 point? Then what's going to happen is this is going to get pushed further into the negatives. So we're going to end up kind of subtracting for each of these digits. It's getting pushed further into the negatives direction. So it's actually going to end up 10 to the -7 in this case. Cool. Anybody have any questions on that? No problem. Let's see what else we got. So of course, last time we also did multiplying and dividing scientific notation. So the nice thing is totally takes advantage of the commutative property. So if you're multiplying 2 things in scientific notation, well, scientific notation is already a number times a number, right? So if I'm multiplying something in scientific notation, then it's kind of like I'm multiplying 4 items together. So if I'm multiplying 4 things together, that gives me a little freedom in how I want to multiply them together. So you can actually get away with just taking the regular integer decimal number that you have out front and multiplying those together. And then the piece where it's 10 to the power, you multiply those guys together. So you end up with some number times 10 to a power, the power being whatever comes from combining those 2 original parts of the scientific notations. So in this case, we end up multiplying the 2.3 and the 9.2 together, and then the 10 to the 5th and the 10 to the -13th together. So the first couple of pieces end up at 21.16. The second couple of pieces, you have to the 5th and to the -13th. They are multiplied together, so you would add the powers. So you end up with 10 to the -8. And of course, in this case, it is not in proper notation. We have 21 point something. We need that decimal point to be 1 digit out, always. So if this guy's to the negative power, it's to the -8, and we looked at this and said, okay, we need to move that decimal point 1 place back. Well, that means that's going to add to that power, so we end up with 2.116 times 10 to the -7th now. It just added 1. Now, without making a big stink of it, dividing numbers follows the exact same concept. So you would just divide the regular numbers together and then divide the scientific notation pieces together. And then, of course, if you end up with a 0.25, you would end up having to fix your notation. In this case, the power would go down by 1 because that decimal point would be going one less digit out from the regular decimal point, from the 0 point. I don't know what to call that. Is that an origin? I don't know. I haven't eaten in 8 hours. I'm starting to get really dizzy. This could be fun. This could be fun. Am I ever going to have a class where I'm not dying for one reason or another? All right. I appreciated that picture way too much. So we got a few examples. I'll go ahead and write them all down because they're not going to be bad. I decided to skip it for this class, but if you ever want to see something ugly, look up adding scientific notation or subtracting because it's so much harder. So much harder. I don't like it. Copying these problems down. It takes too long to write these. I'm just going to write one at a time. That way we're not standing in silence for a really long time. Okay. So for number 1, we have 1.46 times 10 to the 6th multiplied onto 8.2 times 10 to the negative 3rd. I had a multiplication symbol between those in the example. I'm not going to use it because I have 2 sets of parentheses right up next to each other. That implies they're being multiplied together anyway. So just going to leave it as is. So when you're multiplying these, now sometimes I might write out how I'm separating it, but in this case, just make our lives a little easier, right? We're going to multiply these guys together, and then we're going to multiply these guys together. Not bad, right? So embrace Mr. Calculator here. Don't worry about the random transformation of a square root of x. Just helping somebody else with math. So we have 1.46 times 8.2. Okay, so we have 11.972. And then if we multiply these guys together times 10 to the power, that one's a lot easier because if you're multiplying these two together, you just add the powers. So you have a 6 and a -3. So, I mean, guess what we end up with? 3. Now, this one's kind of a tiny scientific notation. Usually you don't worry about it with digits that small because, I mean, if I converted this out of scientific notation, that decimal would move these 3 places and I just have 11,000 and change. So if I already have all my my digits written down, there's no point to scientific notation anymore. But let's just follow through, okay? So we need that decimal point to be after that first digit because, again, we have a 2-digit number in front of that period. So we're going to shift it over by 1, and shifting it over by 1 to the left is going to add to our power. So we have 1.1972 times 10 to the 4th. Okay. I was writing this the other day and I'm like, is this too many review problems? I'm like, think people hate scientific notation enough to deal with the fact that, you know, some extra examples aren't hurting anybody. All right, so believe it or not, we're going to do the exact same thing. We have 6.04, and we're going to multiply that by the other number hanging out there, 3.56. So we get our kind of our standard number part here. So we have 21.5024. And then we're going to do the scientific notation bit. We're going to multiply these 10 terms together. We have 10 to the negative fifth and 10 to the third. Well, you'd add those two together, we end up with 10 to the negative second. Oops, I wrote a 1. That minor brain fart. 3 minus 5 is 1. No. Okay. Now, in this particular case, you're going to see that scientific notation is extra useless, because for us to fix our notation, that decimal point is going to have to move over that one place right there, right? Well, if it's moving over that one place, and we already have a negative exponent, that means this is a tiny number. So that decimal point coming over here is going to go less into our negatives. So instead of -2, moving it to the left, we end up adding 1 to that. So we end up with times 10 to the -1. Which is especially pointless with scientific notation, because you're literally just moving it one decimal away and having to write all of this extra stuff. So in a problem like this, I would probably just go that extra mile and get it out of scientific notation, because it's literally pointless to have it in there if it's this small. Not necessary, right? Now, if I'm doing this, what use is this? Well, if this was a 50 and this was a 35, then it might be a little trickier, right? So this is very useful for very high powers. Makes you do a lot less math and a lot less writing. Okay. Get number 3 written down here. So we have 2.31 times 10 to the 4th. And it's being divided, so I'm going to go ahead and write it as a fraction. So I'm going to have 2.43 times 10 to the 7th on the bottom as our denominator. Hey, hey. Oh, hi.
How are you?
I am spiffy. How are you?
Hi, how are you doing?
Good, how you doing?
Good. Surveys for everyone to take for Hallie.
Interesting. What do I do with the online?
I know, that's what I was thinking too.
That's kind of trickier.
They could email their responses to me if they want.
It's a print off of a Google form.
Mhm.
I just have a link to the Google form.
I don't know how.
That's
You're
fair.
gonna have to come in and share.
That's fair. Okay, well. By 7:30 tonight, so an hour from now.
Whenever you bring them
Okay,
tomorrow, whatever.
that's a little tricky. Okay, all right,
Okay,
all right. How long are you gonna be over
I'm there until probably 7:45 tonight.
there? Okay. All right, well, I have a reason to come back to campus tomorrow, so I'll be here tomorrow.
Okay,
And yeah, so here's what Ben's going to do. Ben is going to take one of these. Give me one, give me one, give me one. They're all gonna end up on the floor. Give me one. I'll hand them out to those here, and then I will type that out and send it to, well, the tricky part is then you end up not necessarily getting, okay. Okay, so
who's
the-
online? You wanna
do
write it
these-
down and I'll send it to him real
do
quick?
these have to be on paper?
No,
Okay,
I don't think so.
are the, for the purposes of this, are the responses being sent in through the form itself?
Yeah,
Okay.
Ellie is using the form. She's got them all on her desk calculating who wants what.
Okay, because I've never seen someone print off a Google form. I'm a little in pain. This is like my mom typing Google into Google. All right, that's what I'm experiencing right now.
I know.
That's what, okay, I'm 100% not gonna have more people than that.
Okay,
All
right.
yeah, I'll figure this out.
Okay.
I'll figure this out.
Or tell them this is a little quiz. And they can email me the answers.
What's your email?
Nicole, oh, you want me to read it? Here,
Yeah,
I'll write
just write it. Yeah, it'll be easy.
it. All right.
A quiz that has nothing to do with math.
Exactly.
Yeah,
Keep up the good work, guys.
all right. Everybody's excited now. Okay, we are going off. We're going off the rails on this crazy train. All right. A worker had that playing multiple times to the speaker. So essentially what's happening is they're thinking of starting a computer class. So, oh, you did?
Have to do again.
Nah, screw it.
I already did one. I'm okay.
Yeah, then you counted the first. Didn't I, yeah, you did it too? Okay. You haven't done it, have you? Okay. All right, so. How am I going to approach this for the online classes? How am I going to approach this? Okay, so this is what's happening. This is what just happened. And why I'm like, hey, what's going on? Oh God, what's happening? So they're thinking of starting like a basics of computer class. I have the incredible feeling that they would start asking me to do it if they do it. I know that's coming. I know it's coming. I'm a freaking nerd. I know it's coming. So essentially, it's just gauging interest. So I'm a little off on how I want to distribute this to everybody online. I think what I'm going to do, is I'm going to type this out. Or I'm literally going to go to this URL and copy paste. I don't know what's worse, honestly. Look at this thing. But I'm going to probably type it all out in English because I might be able to pull off, the Spanish, no problem. But let's face it, I don't know what I'm looking at. Believe this would be This would be in Mandarin, maybe. And this looks Arabic. I think. So yeah, I'll probably just copy this and not type it out in English. And I don't know, attach a PDF version of the form in case that language does not work. But I'm going to send this out as an email later. I am going to CC Nicole on it. So if you guys hit, but I'm going to blind carbon copy all of you. So if you guys hit reply all, it'll just go to me and her. And that is probably the best way to do it. So you're all going to get an email, reply to it. Pay attention and reply to it. Unless for some reason you have gone into the office and they have handed you this and been like, yo, fill this out. Because you already did it, don't do it again. We already have your opinion. You don't need two opinions, and if your opinions are different between one day and another, I am concerned. I'm concerned. So yeah, that's a thing. Cool. The hell was I doing? Oh yeah, math. Yeah, math. All right, cool. I'm teaching you guys math. I've already taught this math. Yeah, and just fill that out before the end of the class so I can like take it in there. Yeah, that'll work. Okay. It's fun. Why not just email everybody a link to the Google form? That would solve some, you literally just open it and click. You know, the library bought a ton of expensive top of the line iPads, and they literally just had us walking around with a Google form on those things. And I was like, really? Really? It was like $800 for this. You could have done this with a $50 Amazon Fire tablet. Really? That's a lot of money. You just got wasted on that. I was like, it would be really useful if we had this app or this app and this app. Nah, just Google form. Expensive Google forms. Okay. Am I done ranting? At this moment, it's going to come back. Let's face it. It's only 6:38. I'm going to rant. It's what I do. I ramble. Okay, so dividing scientific notation. Why does my wrist hurt? I hate today. All right. So dividing scientific notation, we just divide these numbers and we subtract these powers. Because remember, if you're dividing things with exponents, you do the top power minus the bottom power. So same concept, different execution, but it works just fine. So again, we embrace Mr. Calculator. Hello, Mr. Calculator. How are you? Oh, I'm fine. How are you? Okay. I started work 13 hours ago. That's the wrong button. There we go. Okay, 2.43. You know, I've said it before that I tend to type slashes instead of the division symbol because it's easier and the keyboard has that. And I am fascinated by the fact that I have a division key, but even the calculator takes the lazy way out and does the slash. So even the calculator is pulling this crap. I regret nothing. Okay, so we divide those guys. We get funky string of numbers. I'm just going to write them all. 0.950617. Cool. All right, we're done with calculator. We can't do the next part without a calculator. We might be in for a bad time because now we're dealing with the scientific notation bit. So we have times 10 to a power. Well, what power? It's the top power minus the bottom power. So 4 minus 7, you punch punch through the first 4 and you go 3 more into the negatives, you end up with -3 as our power. But this guy is not in proper scientific notation. And if it's not in proper scientific notation, we got to fix it. So that decimal point needs to move 1 to the right. And if it moves 1 to the right, that negative exponent is getting just a little bit more negative. It's getting pushed further to the right. We end up with 9.50617 times 10 to the power of -4. That's a 9, I promise. It's erasable ink on what's basically a dry erase notebook. It's weird, but it works, and I love it. I'll be buried with this thing. No, I won't. I will, in fact, wear out a rewritable notebook. You can even tell weird shapes. Weird glare is happening where I wrote before and it decided to degrade just a little bit. And then we have one more, which I'm just going to tab over and copy for a sec. So the next one is 8.738 times 10 to the 12th power being divided by 1.2 times 10 to the -5th power. Okay. So, believe it or not, we're going to do the exact same thing. Wild, I know. I can barely contain myself. Okay, so we're going to embrace dividing those two numbers. 8.738 divided by 1.2. Hit a random button so it screams. Okay, there we go. We got that thing. Oh, good. Look, it's already in proper notation. It has the decimal point after our first one. So we have 7.28167. Good enough. Totally could have rounded that, decided against it. I don't know why. And then it's going to be times 10 to a power. But what power? Well, again, you have to do the top power minus the bottom power. But you always have to be careful because if you're subtracting a negative, that's going to flip to adding, right? So 12 minus a -5 will change to 12 plus 5. So we end up with 17. 17. So that is my last scientific notation problem. Does anyone have any questions on scientific notation? Multiplying, dividing, converting to, converting from. Random, obscure, weird things that you didn't even think of. Nobody's flailing. Okay. Please move on, Ben. You've told us this twice now. Okay. Well, let's rehash some more stuff from the last class. So, last time we also did radicals and roots. You might say, Ben, why is there the word and? Isn't a radical a root? Yeah, totally. I don't know. Just flows nicer off the tongue. Because radical is the name of that shape that you put over the term, and you're effectively rooting the numbers. So rooting is the action we're doing, radical is the symbol we're using. So roots are the opposite operation of exponents. So essentially, whereas an exponent will make things really, really big, a radical will kind of chop it into a little chunk of it, right? So you can undo an exponent with a radical symbol. You can undo a radical with power. I think I have a couple of problems that deal with that. I hope I wrote down a couple of problems that deal with that. We'll find out in a second because it's the next slide. I don't know. I don't know what past Ben was thinking. So the number that's inside the radical symbol is the index. And if there isn't one there, it's assumed to be a square root. So if you just have the symbol, cool, square root. You have the symbol and the little threes hanging out inside of it, cool, it's cube root. If you have the symbol and there's a 500 hanging out in it, okay, then it's a 500th root. No problem, whatever. So to simplify a root, the easiest way I've found to do it over the years is you determine the index first, so square root, cube root, whatever, and then you find the prime factorization of the number. The index tells you how many of each factor you would need to pull that factor up. You would need to pull that factor out of the radical. Like, did my English fail me? I don't know. So essentially, you prime factor it all the way down. And if it's a square root, you take 2 of each factor. If it's cube root, 3 of each factor, 4th root, 4 of each factor, etc. Scales up forever, doesn't matter. Every time you have one of those groups, it comes out as one of that item. I saw this terrible meme and all I could think of is, yeah, that has to be in the slide. It's just awful, but it's math related. So whatever. I did a couple that have equations. All right, that's cool. So we got a bunch of root examples. I don't like that I made that made number 3 a square root as well. Let's make number 3 a cube root. You know what? Let's do that. That sounds fun. I like that. That's a unique one. Oh, there's a 4th root symbol? When did I deal with that? All right, here's something terrible. Let's just keep doing 64. It's actually a great number to use as an example. Because it's literally just a bunch of 2s. It's 2s all the way down. So let me write out number 1 here. Although I think number 1 is also a bunch of 2s. I think I was just lazy and just wrote a bunch of, multiplied a bunch of 2s together. Okay, so we're going to find the cube root of 4096. I could have started on something simple, but I did something simple last class. So let's do some annoying ones. So the nice thing about these is it doesn't matter how annoying they are, they all solve the same. So what I personally like to do is really cheap, but I will be just horrible. I will type 4096 into my calculator and say, okay, well, it's an even number, right? Let's divide it by 2. Okay. So that's 2 times 2048. It's still even. Do it again. That's 2 times 1024. Do it again. 512. Again, 256. Couple more and we'll get to that 64. 2 and 128. Two and 64. Oh yeah, we're gonna need some room, right? We're still going. 2 and 32. Don't really need Mr. Calculator now, right? It's 2 and 16, 2 and 8, 2 and 4, 2 and 2. Look at all them twos. That's a lot of twos. That's a lot of twos, right? 4096 is a perfect power of 2. Now, we need to find the cube root. So let's find that cube root. Let's go ahead and every time I have 3 of a factor, I'm going to circle it. There. 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 And there. Because every time I circle a group of 3, well, this is now a cube root of 2 cubed. This is 2 cubed. 2 cubed, 2 cubed. So the cube root of 2 cubed is a 2, right? So every single one of these groups, this guy's going to come out as a 2. This guy's going to come out as a 2. This one. And this one. So we end up with 2 times 2 times 2 times 2, which you could either work out or plug into a calculator or be exceptionally lazy and start from the bottom. And once I get all 4 of those 2s, that's a 16. It's a cheap way to look at it, but you know. Now, I'm going to go ahead and delete the problem that's the cube root of 64. Because, hey, you know what the cube root of 64 is? Well, we pull out a 2 and we pull out a 2. So the cube root of 64 would have been a 4. Effort. Not a big fan of effort. Well, let's leave that particular giant number in dust. And we now have, for number 2, the square root of 64. Now, I'm going to prime factor this as well. However, it's 64. I know that's a perfect square. We can absolutely do 8 and 8. That's fine. I could have done that on the 64 in the last one if I saw it. Doesn't matter. Because each of those is going to break down further. And we still end up with, well, the 6 2s that come under it, right? Because, well, under the 64, how many 2s were there? 6 of them. Doesn't matter if I split it into 8 and 8 or 2 and 32, it's going to end up with the same prime factorization either way. So it does not matter. So what do I got? Well, it's a square root. So if it's a square root, meaning I don't have a number right here, that means that every time I have 2 of a number, it's going to come out. So I'm going to circle those 2. I'm going to circle those 2. I'm going to circle those 2. So we end up with 2 times 2 times 2. Or for you eagle-eyed viewers here, who were not clouded by the fact that I'm slowly explaining prime factorization, I could have looked at this and say, hey, what's the square root of 64? Well, it's 8 times 8. Circled that, call it an 8, and call it good. Totally could have done that. Absolutely could do that. You could 100% look at this and say, hey, that's a perfect square. Call it good right there. Totally can do that. You don't always have to factor all the way down. Now, for something big and huge like the last problem, you might not get as lucky. You might not be able to just chop stuff into things that you can tell are going to break down. But if it breaks down like this at all, you can absolutely use that to your advantage. Now, number 3 is the same idea, but in this case, we have the 4th root of 64. So in this case, I've factored 64 enough. We have 6 2s. We've done 64 enough. There are 6 2s there. So what's the 4th root? Well, if it's a 4th root, you circle any group of 4. Cool. Okay, there it is. But then what do you do with the ones that are left? Well, the one grouping is going to come out as a 2. But whatever's left, you have to rewrite the radical and multiply those guys back together, because these guys are still stuck inside the radical. Okay. So all you really got to do, multiply them together and call it good. End up with 2 and the 4th root of 4, which apparently I'm just going to write straight through. Don't know what happened there. Am I having a stroke? I don't know. I don't smell burnt toast. Okay. Let's do more. We're all so happy to have this. We're going to do more. Now, the 4th one is the first one we have with algebra in it. We have the square root of x is 5. I actually considered building an entire lesson around more advanced properties of square roots. That didn't come to fruition because I figured out that a lot of that stuff you don't actually see until college algebra. Honestly, this is probably one of them, but we're going to do it anyway because we kind of have the skill set already. Now, the idea of solving this, normally, what do we do to solve an algebra problem? We try to get the x alone, right? So we undo whatever operations are happening with the side with the x on it until we get the x alone. Well, how do I undo a square root? You square both sides. In order to cancel out a square root, you square it. If you had to cancel out a cube root, you cube it. 4th root, raise it to the power of 4, etc. So you just raise both sides to the power of whatever the index is, because the square root of a square is just that. It's just x. We end up with 5 squared, which is 25. Makes sense, right? Because on the left, if I had the square root of 25, yeah, that's 5. All right. Cool. Well, what else we got? Okay. Number 5, I have x cubed is 27. Same idea, other direction. I have an exponent, and I'm trying to get the x alone, right? So what do? Well, to get rid of that 3, we're going to cube root both sides. Because the cube root of a cube is a x. And the cube root of 27 is a 3. So they're not too bad. Once you have exponents down and you have radicals down, you can put those concepts together and use them. Like actually functionally use them. I have one more horrifying breakdown the radical problem, and then one more algebra one. And then we'll be done with radicals. And of course, I can't write. Okay, so the next one, I have the fourth root of 472,500. We're just going to clean it up. Now, my usual fun bag of tricks, I always like to chop off the part with the zeros first. Makes my life a lot easier, especially in this case, because 100 breaks down real easy, right? So we have 10 times 10, 2 and 5, 2 and 5. Cool. We're already 4 prime factors down. Now this guy over here, 4725, if it ends in a 5, you could divide it by 5. Okay, so I divided it by 5 and we have 945. Okay, well, I could do that by 5 again. I get 189. I have no idea what goes into 189, but I know it's not a 5. So try a 3. Get a 63. Cool. We're good from there. Believe it or not, if this guy's both of its digits are divisible by 3, so totally can break it down by 3. We end up with 3 and 21, which is 3 and 7. So the main thing I wanted to illustrate with the problem like this is, well, how do I keep it organized if I just made this mess? This is a mess, right? I got a lot of numbers here. And it's a little trickier because, you know, I have the fourth root and I have 5s, but they're all over the place, right? So you got to kind of like make a system for that, just to clean it up. You can either do like that one where it's a bunch of 2s and just only use one term or one factor all the way down to break it down instead of doing something like this. Or you could very well, as long as you keep track of it, you could circle parts of it like that. You could do like a weird little blob thing. You could circle them kind of individually. You could do that. But however you want to do it, you just have to make sure you keep it straight, even if it's a horrible blob monster. Because if I do this horrible blob monster, I might lose that too. Don't want to lose the 2. So I know a 5 will come out, but I don't have 4 of anything else, right? So when I go back here, I end up having to say, I have this 2 and this 2, 3 3s, and a 7. So I got a big freaking number in there. So you multiply all those together, and you get 5 and the fourth root of 756. And you might say, what the hell was the point of that? Why did you make us do that? And you still have this big number. Because sometimes you'll look at your answers and you'll see this and you'll see all of these factors and you'll be like, there's got to be something I can do to break that down. There's got to be, right? Not always. Sometimes you just get like a big ugly thing that doesn't much make sense. And sometimes that's just the answer. I always remember in, I think it was a Math 96 book. And they used, like, they kept the problem through multiple editions. So when I was tutoring, I would have so many students come to me for the same problem. And it got to the point where I would recognize it and I would look at them and they'd be like, oh, can you help me with this problem? Let me guess. You got 101/2. You're like, yeah, that's exactly what I got. It can't be right, can it? No, it's right. It's just the ugliest answer. Like, you just look at it and you're like, I gotta be off by one somewhere. Because they wouldn't give you 101/2. Yeah, they would. They absolutely would. Absolutely would. Sometimes you get a weird looking answer. And if you're confident in the work you did, just roll with it. If you're confident in the work you did, you look at it and you're like, you know what, this is totally wrong for sure. Maybe change it. But yeah, sometimes you get an ugly one. You get an ugly answer. Doesn't mean it's wrong, just means it's ugly. Things my mother said after childbirth with me. All right. Number 7. So we have the square root of x plus 2 is equal to 5. Ben, why do you keep using 5? I don't know. It's a small number. I felt like throwing it on the paper. Sometimes I just punch the keyboard, put symbols between them, and see what happens. It works. Okay. Well, what would I do? What would I do? Well, the square root. I can't mess with what's inside because it's stuck under the symbol. So I'm going to square both sides. Now, same thing as earlier happens, but in this case, we still have kind of a more complicated number underneath. That's okay. Because once you square both sides, we have a nice looking problem, right? X plus 2 is 25. Cool. Subtract that off. We get 23, and we're happy. That's it. I lied. I want one more example. Because I thought of something that would be a good example. Because say I had, I don't care, cube root of x minus 1 plus 3 is equal to equal to 7. Let's say I have the cube root of x minus 1 plus 3 is equal to 7. And notice that that radical stopped above that 1. So that plus 3 is outside of this symbol. It is outside of that little function thing going on there, right? So can I cube both sides? If I cubed both sides right now, it would take an advanced level of math that would suck for both of us. This would be very annoying to deal with, right? And I don't think it would work out nice. Until I get rid of that 3. if I isolate that radical on one side, if I get that thing alone, where that is the only piece on that side, that's where we can use the exponents to cancel it out on both sides. That's where we can do that. Until then, you don't want to do that to an entire side because it wouldn't distribute. It would actually say, I have this thing plus this thing multiplied by itself 3 times, which is honestly kind of horrifying to think about, and I don't want to do that math. So you get the radical alone, you get rid of the radical. 4 cubed, 4 times 4 is 16, 16 times 4. Oh my God, I put it in there again. There's that freaking 64. And then we can add 1 both sides. So we get a 65. So those are applications of radicals and exponents. Do we like them? Do we hate them? Are we concerned? Are we concerned about the future of our lives?
So if that was a x1, x minus 1, -3, so you would add it instead of subtract it, right?
Exactly.
So,
Yeah, and then you would end up with 10 cubed, which would be 1,000. So you can see that they, the thing about how the numbers would jump up exponentially, that this is literally the definition. It's an exponent. So the number jumps up exponentially. That's where it comes from. It's just jumping up like crazy. Okay. So that's pretty much all we got for those. Are we happy? Are we not happy? Are we concerned for our lives? Good. I think everybody's moderately okay. Okay. So now that I've wasted half of the class talking about the old stuff, let's do new stuff. Lines in the coordinate plane. So a lot of people are concerned by graphing, and it's really not so bad. It's really not. There's just, some guidelines to keep it straight. No pun intended on being a graph. I hate myself for that one. All right. So all linear equations can be shown as a graph of a line, right? Makes sense. Linear line, there we go. So it's represented on a Cartesian plane. You'll see it written as a Cartesian plane. You can see it written as a coordinate plane. Its proper name would be a Cartesian plane because that is describing the type of plane it is. But until you do trigonometry, you're not going to see another type of plane. Because then you start playing with polar coordinates and all kinds of weird stuff that have great uses, and some things are really simple doing them that way, but in this particular structure, we're just rocking lines. So this is made up of 2 perpendicular number lines. Perpendicular meaning they're 90 degrees from each other. So one's going straight up and down, one's going left to right. The x-axis is the horizontal one, left to right. And the y-axis is the vertical one, down to up. So left and down are negatives, up and right are positives. The very center point is 0, 0, and is referred to as the origin. So if you're ever told that something is so many units from the origin, then you're like, okay, I'm just going to start from the middle and count out. Okay. Oh, we got a lot of slides before I get to actually doing anything. Cool. Lots of explanation. Love explanation. So how to graph using the Cartesian plane. So this is just going to be how to graph a point. So whenever you're given a point, it's usually in the format where it has a set of parentheses around two numbers separated by a comma. The two numbers are always in the format x comma y. So you're always given the x part of the coordinate first, the y part of the coordinate second. So what I usually do is I kind of put my pen at the origin. There's, for those online, I think there's an annotate mouse. Select spotlight. Yeah, people could see that. There's a spotlight. Okay, change its color. I want to change its color. Oh, Zoom. You guys suck. Nope, can't change its color. Okay. So you would start at the origin and you move left or right along the x-axis to the x coordinate of that point. So we have 3, 4. So that's 3 in the x direction. And then you move up or down according to the y coordinate. In this case, it's 4. So we go up 4 and we draw our dot. Usually you'll also label that point on your graph. Couple of reasons. One, it lets you be able to see, like if it's a graph that's being referenced, people can look at this and say, oh, that's 3, 4, rather than looking at the point and counting along the origin to try to figure out what that point is. The other point I like to use for it is that if you are going back and checking your work, you would look at that point, and sometimes I will see that 3, 4 off at the point 4, 3. That is the most common mistake I see with these types of problems, is people swapping the x and y. So just be careful of that. Now, graphing a line, let's look at example 1. So in that graph, that is the equation that 3x plus 2y is equal to 4. So it's a standard form of a line, which is an ax plus by equals c form. Future reference, you're not going to have to worry about that. I've always laughed about this, but as long as I've tutored math, I've never seen, like every once in a while, you'll see a problem that says, leave this in standard form. And it's like, okay, cool. All that means is put all the x's and y's on one side and get rid of the fractions. Whenever you're actually using standard form, you really don't think about it. You don't have to think I'm working with standard form. You just, that whatever it is that you're working with, you know, is going to be set up that way. So memorizing ax plus by equals c is completely pointless and completely unnecessary at this point. So the idea with a straight line is that every single point along that line makes that equation true. So if you plugged in an x to that equation and solved it for y, you would get a point on that line every single time. You could plug in 5 million into one of those and you would find a point on the line. Would you want to graph that point? God, no. Terrible idea. Terrible idea. But it's possible. So how do we make a line? Well, usually you plot points. That's the initial way you usually do it. So what you end up doing when you first start doing these, you're usually given a bunch of points, and then they kind of slowly push you into making your own points up. So what you end up doing, you always have an equation. And I was kind of fascinated because I went looking into different explanations online on doing this plotting points thing. And I had already typed out this equation, and I found that a great many people who are writing how to graph by plotting points or how to graph in general use y equals 2x plus 1. I don't know why, but it's the most natural. It's the most natural equation that math people seem to pull out of their bag of tricks to teach this. So I thought that was weird. So the idea is that you are going to find sets of points on this line, put them all on a graph, and then draw a line between them. So remember evaluating expressions. This is a good example of when you would use evaluating expressions. You're trying to find, you might have an X already, you're looking for Y. So we have these values. Let's work at it. So this first line here, this is just my explanation on why I picked these small numbers, because like I said, you could plug in 5 million, but you're going to hate your life graphing it, right? So I like to keep whatever points I'm graphing really close to the origin, because if they're really close to the origin, those are going to be the smallest numbers that this thing's going to spit out, right? At least at this point. If you have your graph really far off to the side, then it's a terrible idea. But we keep it pretty close to where it's crossing an axis, right? So you're going to use the equation, substitute these values to find the corresponding y values. So you do that. For example, when that first one, that x is -2, you take that -2 and you just plug it in for the x. So you would have 2 times -2 plus 1. So you multiply the 2 by the -2, you get a -4. You take that and you add the 1 to it, so you end up with a -3. And that is the first line of your chart. After this, you would plug in the 0. Bless you. You plug in a 0, the 2x goes away, you just have a 1 left. And then if you plug in a 2, you have 2 times 2 plus 1, that's 5. So you get a bunch of points. You plot them all on your graph. Exactly like we did before. So -2, -3, you go to left 2, down 3, draw a dot. Next is 0, y is 1. So if x is 0, that means it's on the axis. You're not going left or right at all. You're just going whatever the y is going to take you. So it goes up 1. So you're on the axis right here at 0, 1. And then 2, 5, you go 2 in the to the right and up 5. So you got your points. All you got to do with the points is draw a line between them. Problem solved, we have a line. Now, you might say, hey, can't I just draw 2 points and make a line? Yeah, you can, if you're sure of what you're doing. So when you first start doing all of these, you usually do 3 points. And the reason for that is just to be able to check your work. Because if you draw 2 points, any 2 points on any graph is going to make a straight line. But if you draw that 3rd point and it's not on your straight line, you made a mistake somewhere. So that's why they usually have you do 3 points when you're starting to graph these, because you could totally make a big mistake and blow stuff up. Also, this picture is way too accurate. You ever had a kid just stare at you like that? Usually in a shopping cart while you're standing behind the parents in line, just staring deep into your soul. Like, what is this kid having? It's horrible. It's horrible. Okay. So we got some examples. I don't know if I'll do all four. I would like, very much like to graph or cover the next concept as well. Nah, we'll do all four. It'll be fun. We're gonna have fun with this. So y equals 3x minus 2. That's gonna be our first one. Okay. So y equals 3x minus 2. We're gonna find some points along this line and then we're gonna graph them. So usually what I like is that this guy's already set up as y equals, which means whatever I plug in over here is gonna spit out my y. So that's gonna make my life a lot easier. I appreciate that. And that means I can very safely pick some numbers to throw at my x. Now, if there's one thing I've wanted to do in my life, it's throw things at my ex. All right. So we're going to keep these numbers nice, simple, neat, close to the origin, make our lives a little bit easier. So I like to plug in. A lot of times you'll just see me do -1, 0, and 1. That is like my go-to because those are, you know, on the axis and really close to it. Sometimes I won't do that. That's usually when I have like a fraction up here. I'll show you how to deal with that. I'm fairly certain. Of course I didn't. Nope, totally didn't do a fraction one. Okay, well, that's fine. Not the end of the world. All right. So for each of these, you're going to plug in that x and find the y. So in this case, you would have y is equal to 3 times, and instead of x, we have a -1 minus 2. So you cleaned it up, work it out. 3 times a -1 is a -3. -3 minus 2 would be a -5. All right, no problem there. You'll figure out really quickly that plugging in a 0 is great. Plugging in a 0 always makes life easy because whatever it's multiplied onto is gone. All we have left is that -2. And then if I plug in a 1, so 3 times 1 is 3, minus 2, 1. Cool. Now, I've always been really cheap about how I graph things. Sometimes you'll have teachers be like, no, you have to meticulously draw check marks for at least 10 in every direction. I hate that. I hate that. That's too much effort. What I usually do is I look at my ranges. I'm like, cool, this one goes from -1 to 1. So how wide's my graph? About that wide. There we go. I don't care. It's gonna be, you know, maybe we can go a little bit more. This is a little ridiculous. And then my y values go from 1 to -5. Highest it goes is 1. Cool. All right, there it is. And then we're going to go down to -5. Okay, I had a stroke. I don't think anyone who's great at math ever excelled at drawing straight lines. 1, 2, 3, 4, 5. So the main things to keep in mind are that you really want to make sure that the spaces between your check marks are as close to the same distance as possible, just to keep everything straight. Now, in order to graph these points, we start with the X value and then go to the Y value. So our first one is -1, -5. We're gonna go back 1 and down 5. There's our point. Label it right next to it. And then we have the point 0, -2. So it's not going left or right at all. It's on the axis and it's going down 2. So that's 0, -2. And then we have the point 1, 1. Love it. 1 in the X, 1 in the Y. There it is. 1, 1. And then you look at it, are all of our lines along, or points along a straight line? Yeah, absolutely. So we draw a nice, hopefully straight line between them, and we call it good. That's our graph. Isn't it beautiful? It's a beautiful graph. Let's do more. Let's do a bunch more. Let's do 1,000 of them. I'm gonna do 1,000 of them. You guys don't need to go home. We're just gonna stay here and do math forever. It's what everybody has always wanted in life. So what I'm going to do for number 2 is I'm going to show you one of my go-to strategies for plugging things in. Because when it's like this, when it's in standard form, I hate plugging things in. I hate it. Because if I plugged in something for that X, then to solve for Y, I would have to subtract 2 times whatever over to here. And that's how I would solve it. Every single time I would have to make that adjustment, right? So what I like to do is I like to solve the equation for Y right away. If I subtract the 2x from both sides, and I have Y is equal to -2x plus 2. Notice I put the term with the X first, even though you could have written it 2 minus 2x. I write it this way, 1, because it fits a formula that we're going to be hitting in a slide or two. And 2, because it works out a little nicer usually. But if you solve that for Y, then the effort you're going to put out for finding your points is about the same as the last problem. So that way we don't end up having to subtract 2 times whatever every time. We just did it once and we never have to do it again. So we can plug in whatever points we want. We can plug in 0, 1, and I don't even care. We can plug in a 4. It doesn't matter, because every single one of these, every single number you can plug in for X is going to spit out a Y. So it doesn't matter what you pick. It's just a question of where you want to graph. So every one of these, you're just going to plug them in. And work them out. -2 times nothing is nothing. Plus 2 is 2. -2 times 1 is -2. Plus 2 is nothing. -2 times 4 is -8. Plus 2, -6. So we got some points. Let's throw them at a graph and see what sticks. So in this case, my X's go from 0 to 4, my Y's go from 2 to -6. So we're going to be off to the right and not too far up, but pretty far down, right? One, two, 3, 4, 5, 6. That's all I care about. And 1, 2, 3, 4. That's all I care about there. Remember, that's our X, that's our Y. So let's graph the points. We have the point 0, 2. So 0 on X, again, not going anywhere to the left or the right, but 2 on the Y means we're going to be right there. 0, 2. Then we have the point 1, 0. That's 1 in the X and nothing in the Y. So right there. And then we have the point 4 and -6. So we go out 4, we go down 6, we have our point. Yeah, those look like they're along the line. We're pretty happy with that. There we go. It's a line. How are we feeling on these? Is everybody feeling okay? Do we need to see more? Do we want to see more? Do we need to see what we do? Oh, sorry. Go ahead. I know you said something, but I don't know what you said. Can you repeat it?
I just, yeah, I need to see a little more, if you can.
That sounds great. Let's do this. So I'm going to change one of these problems. There we go. That's going to cover something I want to cover. Number 3, we're going to have 2x plus 4y is equal to 8. Okay. Two x plus 4y is equal to 8. Now, just like that last one, I'm going to solve this for one of my variables to get it alone on one side, just to make our lives easy. Usually you solve for y. So that's what I'm going to do. So we're going to get that y alone on the left side. So we're going to subtract the 2x from both sides. I end up with 4y is equal to negative 2x plus 8. And then in order to get rid of that 4, we have to divide by both sides, right? But I have multiple things over here. So what we have to do is we have to divide every single individual thing by that 4. Now, perfectly fine for this guy, but right here, it gets a little messy, right? Now, what I like to do is I like to, first of all, consider this as a fraction and reduce it. 2 over 4, that's a half, right? Now, I'm going to keep that negative on top, just for funsies. It also ties into another strategy I have for the next concept we're going to cover. So I just kind of like having the negative on top. But the x, that doesn't need to stay on top. That can actually come out. Anything that's on top can come out to the front, to the side of it, right? Because this is still this would still, if I put this over a 1 and multiplied it in, it would still end up on top. So I pull the variable out to the side. Then I break down my 8 over 4. So that's our new equation. And now you can see that if I started plugging things in for x, what's going to happen? I'm going to get fractions, right? So here's the thing. I run gung-ho into fractions. I like to cram them in wherever I can. But when you are graphing, you want solid numbers. You want exact points along those graphs. You don't want to graph fractions. You don't want to graph decimals. Nobody does. It's a bad idea. So avoid them. So, well, how am I going to avoid them? If you pick things that are divisible by the bottom of this fraction, then it's always going to end up a solid number over here. Now, that would get complicated if I ended up with some weird fraction over here. There are strategies to get around with that, but honestly, you're probably just going to punch in the calculator and eyeball a decimal and call it good. But you're also not going to do this often enough that you will run into that. I don't think you will ever run into that. So what I would do is I usually go with my go-tos, the -1, 0, and 1. I'm not going to do that because that's going to give me fractions. So what I'm going to do is I'm going to do -2, 0, and 2. Because each of these, I mean, 0 doesn't much matter, right? But each of these are divisible by 2. So I could say, what's half of 2? You know, that makes my life easier. I could plug in a 4, I could plug in a 6, you know, whatever even number I want to plug in is going to make my life easier. So it's all about just making your life easier to find these points. So I'm going to go ahead and plug them all in. So -1/2 multiplied onto a -2. Negative times a negative gives us a positive. Half of 2 is 1. So this is a positive 1 right here. So you take that 1, add it to that 2, we end up with a 3 right here. -1/2 times 0. I love it. It's gone. That whole thing is gone. We just have this +2. If you see the relationship between these two numbers, you can probably guess what's going to go here. -1/2 of 2. Half of 2 is 1. So this is -1 plus 2. 2 minus 1 is 1. We get 3, 2, 1. This guy's going down, right? The y values keep decreasing. That actually is something that always happens when there's a negative right here. The values always go down. If it was a positive number, the values always go up. We are going to cover that in the next slide. So let's graph them. Here's some good points. Let's graph these. I want to cram the graph up in the top right, so I have room for the other problem. So draw my little graph. It's cheap, but it's going to work because it's 2 in every direction on the X and 3 in the direction of Y, and we are peachy. That's our graph. It's going to be cheap, but it works. So again, we start with our point. We have -2 and 3. So go back 2 and up 3. There we are. Then we have the point 0, 2. Oh, I forgot to label it. When you get to higher level stuff, you usually stop labeling them. because you end up with squiggles. You don't want to label everything along a squiggle. So we have 0, 2. That's going nowhere in the X and up 2. And then we have 2, 1. That's 2 in the X, 1 in the Y. So it is going straight down at a more gradual pace than some problems. Because, you know, it's only going down for each one, it's only going down a half. When it moves over, it only goes down in half. Now, that's actually going to come in really handy conceptual wise in a moment. Let's do number 4. Next one I have is y equals 2x minus 4. Okay. So it's already pretty straightforward. It's already y equals for us. So let's go ahead and throw some values in there. Now I'm going to show you another way to do these. Participants can now see your application. You scare me, Zoom. You scare me. I should have seen it before I started the class. There's apparently 3 microphones hooked up to this thing because the document scanner has one. I think the big camera in the back has one. There's microphones in here. So the computer kept freaking out and jumping between them. And I just had like 1,000 boxes popping up in the center of the screen. Like, it is now switching to this. We are now switching to this. We are now switching to this. So I hope it doesn't break anything, but I went into the device options and I disabled all the other microphones. So if I hit this power button, nobody will be able to hear anyone in this classroom. Am I going to fix this before I leave? No, that sounds fun. We're just gonna let it happen. Yeah, I'm a terrible person. So we're gonna graph some points. What do we want to plug in? Anybody want to throw numbers at me? What do we want to plug in? Does anybody care?
357.
357? 357. Yeah, those aren't gonna suck. That's cool. I like it. Those are good numbers. All right. So we're gonna plug them in. You might say, Ben, why do you keep writing them all out before solving any of them? So you can kind of see the structure. It's all the same thing. We're just plugging in some numbers. Same spot every time. All we need to worry about. Okay. 2 times 3 is 6 minus 4. That's a 2. 2 times 5 is 10 minus 4 is 6. 2 times 7 is 14 minus 4 is 10. Okay. Well, we're going out decently in both directions. Both in the positive direction. So I'm not going to plug in. I'm not even going to draw my negative directions. A lot of times I'll have just a little poking out in both directions so people don't look at this and imagine it's some kind of weird other type of graph. So my x's, I have 3, 5, and 7, so it needs to go out at least to 7. And y is going to 10. Just barely. Okay. So let's graph it. We have the point 3 and 2. So we go 3 in the X and 2 in the Y. We have the point 5, 6. So we go out 5 in the X and 6 in the Y. 1, 2, 3, 4, 5, 6. And then we have 7, 10, which I definitely know where that is because that's as far as my graph went out. A little cheap, but makes my life easier. So that's why I do it. Those all look like they're along the same line. So we draw it between them. And we call it good. Now, as a preview for graphing the slope and the intercept, because that's going to happen here pretty soon. Without all of this work, there is another way of doing these. This is my preferred way of doing these. And I absolutely could have looked at this equation, gone down 4, and plug up, just eyeballed some points and gotten the exact same graph. That's what we're going to be learning. We excited? Yeah, we're excited. So let's switch over and learn it. So before we get to that particular method, we have to understand some parts of it, namely the slope. So the slope, this is stupid useful. You write anything down today, write that thing down. You're going to use it. So the slope is effectively, it's kind of the angle. It's how it angles away from like the horizontal on the X. So it's, you know, you can think of slope. What do you think of when you think of slopes? You think of skiing, right? You got like an angle downwards. That's pretty much what's happening. We're finding the direction that the lines are sloping to. So it's found using 2 points from any line and plugging them into that equation. Now, once you start having those little subscript numbers, people start getting their eyes glazing over. And I get it, but all you really got to do is look at this thing and say, okay, well, those are just 2 separate points. So you're basically have 2 points where you have X, Y. And since you have 2 points, you're going to say that one of them is X1 and Y1. Just saying, hey, that's point number 1. And the other one is X2, Y2. So that's point number 2. That's all that's really saying. So generally, slope can be thought of as rise over run. That's actually really, really useful for graphing purposes. So it's good to keep that in mind as well, that slope is rise over run. Because the change in Y, the top part there, difference in those Y's, is the rise between 2 points. And the change in hi, typo, that I don't think I've caught in the last year of teaching this. Oops. The change in X in the denominator between the X2 and the X1, that's the run between the points. So rise, height, over run, width. It's really useful, really, really useful. So again, I've had people whose eyes glaze over when they see the next slide. Do not fear this big ugly thing. The big ugly thing is literally one of them solved out with every single step in one line. So finding the slope of a line. So let's go back to the example y equals 2x plus 1 and take a couple of the points off of it. So a couple of the points we had were -2, -3, and 2, 5, right? So it doesn't matter which points you pick or in what order they are, as long as they're on the line. I don't care if you pick something 500 out to the right and then right smack dab on the 0. As long as there are 2 points on the line, you will always get the same answer from this equation. Does not matter what they are. You can reverse them. Like in this particular example, I used the second point as x2, y2. If I flipped this thing around, I would have the exact same answer. No exceptions every time. So in this case, you are going to designate your points. So since I wrote the -2, -3 first, I decided those were x1, y1. And then the other one is x2, y2. So you could see that on the second step, what you end up doing is you subtract the y values. So we're do a 5 minus a -3. And on the bottom, we have to subtract the x values. If you started with with 1 point on the top, you have to start with the same point on the bottom. As long as you keep that straight, you are good. Just memorizing rise over run, it will work out. So on the bottom, we did 2 minus a -2. So you can see that that cleans up a little bit. In the next step, you end up with a 5 plus 3 over a 2 plus 2. So you have an 8 over a 4, which is just 2. You can actually see that 2 hanging out in that equation. Usually you will use this equation to find the slope between 2 points only when you don't have an equation. And the reason you only use it when you don't have the equation is because there it is right there. In the standard slope-intercept form of a line, which is the way I prefer to do it, not the ax plus by thing, but when you have y is equal to something x plus something, whatever the heck is attached to that x is your slope. That one right there is where it's going to cross the y-axis every time. So this is a problem I could have just eyeballed. Going back to the notes on that last problem, and I was like, hey, look, this is a way I could have looked at this. What I did was I said, okay, this -4 means I'm going to start at -4. And then I moved upwards based on the slope. It goes up 2 for every 1. And you'll see that a little bit better in a minute. Just based on that, I can skip all of this. Sometimes you don't want to. Sometimes you have something ugly or you have a particular reason where you don't want to use that method. Maybe you have really ugly numbers. Maybe you'll have something called a piecewise function where you have multiple chunks of different graphs as one big ugly graph. That's an option. Sometimes you just don't want to do it that way. And I will tell you that as far as you go in math, you can get up to differential equations after Calc 3. And if you have to graph something ugly, you're like, I don't know, I'm just going to plot a bunch of points. You 100% would do that. So that is like universal method of what the hell does this look like? So the slope-intercept form of a line. The slope-intercept form of a straight line is written in this way. Y equals mx plus b. I swear I centered that when I typed this out. So it's called the slope-intercept form because m is the slope and b gives us the y-intercept. So the y-intercept given as a point would therefore be 0, comma b in parentheses, since the y-intercept, it's intercepting the y-axis, which means its x value is 0 because it's not going left or right anywhere. It's just hanging out in the middle there. So the y-intercept is technically, it is always a point like that. That is something that is given the greatest amount of leeway when you're learning this stuff, because honestly, you don't see it written that way very often. You just say, oh yeah, the y-intercept is whatever that number is. Most of the time, that's what you're going to do. So let's find some slopes. Let's find some slopes. So I'm going to write out some of these points. I'm going to show you how to do them. And it's not particularly hard. It's a little weird at first. But it's not bad. Cool. So for this first one, I'm going to go ahead and rewrite the formula. So you have m, and no, I don't know why slope is always m in math. I have literally no idea. I don't know why they rock the m. It's their own thing. Let them have it. So it's always y2 minus y1 over x2 minus x. So what are those? Well, doesn't matter. Let's just pick this one as x1, y1, and this one as x2, y2. Right? Now just plug them in. So it's going to be this minus that over this minus that. And notice how I did that. I started over here and I went to this one. And then on the bottom, I still started over here and went to that one. As long as you keep that straight, you can get away with flubbing this. As long as you know it's the change in height between 2 points over the change in width between 2 points, you're good. So just work it out. 5 minus 2, 3. 2 minus a negative 3. Remember, that's going to end up adding. So we end up with a 5. So our slope on that one is 3/5. And again, it doesn't matter if I had flipped this guy around at all. I would have ended up with 2 minus 5. So I would have ended up with a negative 3 over a negative 3 minus 2. Negative 5, you would have had a negative divided by a negative. It would cancel out. You would still get 3/5. Does not matter which order you pick them or which points along the line you go with, ever. Speaking of, here's this one, just for illustration purposes. Let's just decide this is the second. This is the second one. And if you're feeling confident with it, you don't even need to label them. You can absolutely just say, okay, I'm going to do this minus that over this minus that. Works out. Right? So we end up with negative 6 over negative 8. Well, the negatives cancel. And this reduces, right? So we end up with 3 over 4. Okay, didn't mean to do that. Okay. Let's do more. How about this guy? Same thing, except this time I'm not gonna label them. We're just going to do it. What's our slope? Doesn't matter which point I start from. It's always the y minus a y over an x minus an x. So let's just do this minus that. 3 minus a negative 1 over this minus that. 7 minus 6. Okay. Well, again, subtracting a negative ends up a positive. We end up 3 plus 1, 4 over 7 minus 6, 1. Oh, cool. It's over 1, right? So we don't really need it over 1. We can just say it's 4. Problem solved. So generally, that's how much effort we're putting in. It's not too bad. Let me write down. Oh, that was bad. Let me write down the next couple. Yeah. So number 4 is going to be fast. You're going to see why I like things with zeros in. Because if I just do this point minus that point, this y minus that y, negative 1 minus 0, okay. This x minus that x, negative 1 minus 0. Well, cool, what do I have? Well, this is just a negative 1 over a negative 1. Negatives cancel. 1 over 1 is, well, the whole thing's just 1, right? And that's actually, let me show you the graph of that one real quick. It's actually like a very standard graph. It actually goes a perfect diagonal like that. This is the graph of y equals x. It's just something you see every now and then. Really easy to graph. It's just a diagonal line. Okay. How about this guy? Let's do that one. Let's do this minus that. So remember, I'm doing, so this is an x, this is y, this is an x, this is y. So I'm going to do this y minus that y. 0 minus a negative 8 over this x minus that x. 5 minus 0. So up here, I end up, I know I got a 0. I know you wouldn't normally think of what's going on here, but you do have a negative of a negative 8. That's what's happening there. So you still have to look at this as kind of becoming a positive. So it's an 8. Down here, I like that. 5 minus nothing is a whole lot of 5. So 8/5. Okay. All right, gotcha. Okay. So we're still identifying the slopes. I'm going to write all of these down. Here's all of our problems. Look at how much room I gave us. I wonder how quick this is going to be. So the idea on finding the slope on an equation is that you want it in standard slope intercept form. So let's look at that formula. Y equals mx plus b. So we have y equals, so we're solved for y. We always lead with our term with the x. Notice I did that on the earlier ones where we were plotting points. This is y, it's just getting it into this form. And then plus b, some number, right? So the m is always attached to the x. Whatever's on the x, that's your slope. But this first one's not in standard form, right? So we got to solve for y equals. Just like we did on some of those plotting the points ones. So I'm going to subtract the 2x for both sides. And again, just like that one I did earlier, I'm not going to write 2 minus 2x. I want this in our standard form. I want this in slope intercept. Now at this point, I can identify what the slope is. It's whatever's attached to the x, right? So it's just a -2. Okay, so the next one, what's the slope? Somebody yell it. Is everybody just tired and want to go home? I know I am. Hey, thank you for not leaving me hanging. You're right, it's 3. Because it's the thing on the x. So, okay, what's the next one? 2, right? Just the thing on the x. Cool. What's the next one? It's in standard form. Well, standard slope intercept form. I gotta stop saying standard form because that's that weird ax plus by thing. Next one, we have -1/2 x plus 2. Well, the thing on the x is -1/2. There we go. That's the effort, right? So what do I do on this last one? Same as we did on the first, solve for y. Subtract the 3x over. We have 6y left on this side. Put the -3x first. Plus the 18. Don't forget it's plus 18 because this guy doesn't have a negative, which means it's a positive 18. And now we divide everything by 6. And I will have y is equal to, this will reduce, we end up with -1/2 x plus 3. Hey, look, it's almost the exact same line as the previous example. We have the exact same slope. If I was to graph these two lines, they would be parallel. They'd be running right along each other. They would never cross. Any two lines that have the same slope are never going to cross because, you know, they're going up and down at the same rate. They're not going to change course, you know? So that's finding the slope. How do we feel about finding the slope? Is it okay? Is it terrible? Finding it in an equation, nice and easy. Finding it in points, a little tougher, right? So before we get to graphing a ton of graphs, I think this is a good stopping point. Because the next thing I would have to do is graph 5 graphs, and I don't want to devote about a minute to each of those. So we're gonna call it good. We're gonna pick up next time with some review, of course, and then actually graphing with the slope. So the slope is really great, and it's really quick, and it's not bad. So, yep, calling it good. Everybody have a good night.
So this thing is just a basic computer class.
I think so.